Let's now have a look at some revision questions for the practical aspect of Physics Paper 3. So the first question says the apparatus in Figure 7 is used to determine the mass m of a load using the principle of moments. A uniform metal tube of weight W is kept horizontal by a supporter P and by a vertical force F applied by a force meter Q. Now P and Q are at the same distance from their respective ends of the metal tube. A load of mass m is suspended from the metal tube at a distance a from P. The distance between P and Q is B, so the distance A is varied over the range of 0.100 meters to 0.700 meters. The force F needed to keep the metal tube horizontal is measured for each value of A. Throughout the experiment, B equals 0.800 meters. So show by taking moments about P that F equals mg over B times by A plus W over 2. So pause the video now, then when you want to go through the answer, unpause the video. Right, so how do you answer this particular question? Well, it's understanding what the principle of moments is. And it's the idea that because it's being kept horizontally, we must know that the moments clockwise will equal the moments anti-clockwise. So what we can say is how to work out a moment is going to be the force times by the distance from your particular point you're taking your moments about, which in this case is P. So we know that the anti-clockwise moment is going to be F times by the distance of B, because that is the distance, if you see previously, between F and P, and that is causing an anti-clockwise moment. Now in the next point, what's causing our clockwise moments? Well, it's going to be M. Okay, but that's not the force, that's just the mass. So the force is going to be mg, it's going to be the weight. So it's going to be mg times by a distance of A, and it's also going to be W times by B over 2, because what in fact is W? It's the weight, and you should always remember that for a uniform object, there's going to be a weight acting at the center of mass, which we can consider to be the center of the object. So that's going to be B over 2 away from P. So you add those two ideas and you equate them to the anti-clockwise moment. You can then rearrange to make F the subject, and you get your answer out. The next question now says that figure 8 is a plot of F against A. So draw a best fit line on figure 8. So pause the video now, then unpause the video when you want to go through your answer. Right, as we'll see throughout this particular revision session, it's a very common question to ask you to draw a line of best fit on graphs. So here you should be looking at a good line of best fit. So it should be accurately following the trend with an even scatter of points on either side. So you'd be looking at an intercept of tracing it back through of about between 1 and 1.2 newtons. Now the next question says, from this idea, determine M. So you might need to look back onto the previous screen to see that, and then the force meter has a 0 error. Determine using figure 8, so from the previous screen, a value for the 0 error when W equals 2.6 newtons, and then explain whether the 0 error in the force meter has an effect on the value of M calculated in the previous question. So pause the video now, and you may need to go back to the previous screen to look at the graph, and then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you should see that if you look back at the graph here, we've got F over A, so we should know that the gradient of F over A, okay, is going to be in this instance, okay, as you'll know that in this idea that A is in fact the distance, okay, between the mass and point P. So as a result, you've got a distance and you've got a force there. So at that point, what you can do is if you work out your gradient of your line as seen here. Now remember, when you're working out a gradient, you need to draw your gradient triangle on the graph and make it as large as possible. Then you should work out your gradient. So at that point we know that our gradient is going to be a force over that particular distance. So what we can then do is we can then use this to work out the calculation of M in mass, and then you can work it through to be about 0.65 or 0.68, because what you can do is if you look back, you can work through, okay, what the value is going to be from the previous equation to work out your value of m. So you get between like 0.65 and 0.68 kilograms. Again, it's very common in paper 3 style questions for you to have to work out values from equations given to you. Again, determine in the next question a value for the zero error. So again, you can see quite clearly that the zero error manifests itself, okay, as it doesn't go through the origin, it'll go through part of the y-axis. So you've got to find your idea of your of the graph to find the zero error. So you get about 1 to 1.2 newtons. It's the y-intercept, and then what you can do is then use that to then work out what the value and the weight is going to be. So you get an error in about 0.2 to 0.6 newtons. Now, will this affect the mass? Well, it won't affect the mass, because as you mentioned before, a zero error will affect the y-intercept or the x-intercept for your graph. It will not affect the gradient, so therefore the gradient is unaffected, and the gradient is what we use to ultimately calculate m, so would not affect it. The next question says, technetium-99 is a radioactive isotope used in hospitals. Identify the type of radiation that is emitted when technetium-99 nuclei de-excites. Then, samples of technetium are prepared at a hospital from a source of a radioactive isotope, molybdenum, that is stored at the hospital. Figure 9 shows the generator that is used to prepare the sample of technetium. Water from a syringe passes through the molybdenum sample. A technetium-99 that forms from the decay of molybdenum, okay, dissolves in the water. The water containing technetium is collected in a lead storage container. Explain how the apparatus in figure 9 allows the safe handling of the collected sample. So pause the video now, then unpause the video when you want to go through your answer. Right, there will be certain questions which link into just knowledge and understanding from paper 1 and paper 2 on paper 3. So the first thing you've got to be aware is, as the technetium de-excites, because it's in a metastable state as indicated by the M next to the 99, it will be emitting gamma radiation. Now again, the paper 3 questions can sometimes ask about safety procedures needed for experimental procedures in physics. So how do you know it's got the safe handling? Well, the generator is shielded with lead. It makes a big deal of showing the fact that it's a lead storage container, so that's a very important idea. So this reduces the amount of radiation the user is exposed to, because some of the technetium will be releasing gamma radiation, and some of this gamma radiation will be blocked by the lead. The next question says, figure 10 shows the variation of the activity of molybdenum in the generator over an 80-hour period. A0 is the initial activity of the molybdenum in the generator. Estimate the half-life of molybdenum. So pause the video now, then unpause the video when you want to go through your answer. Right, so you've got to be able to work out values from graphs in physics paper 3 questions. So what you should be able to see is, you've got a value for A0. So what you can then do is you can use this to work out a value for A0 over 2, which will then give you the half-life. So if you look to see how many squares it goes up to, so you can see that A0 goes up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So therefore A0 over 2, or half that, will go up to 5 squares. You can then read that across and you'll see that it's just over 64, so therefore it will be 66 hours. Now the next question says, figure 11 shows the activity of the molybdenum, and then a sample of technetium-99 is collected from the generator every 24 hours, causing activity of the technetium in the generator to fall to 0. Sketch on figure 11 the activity of the technetium between the 24 hours and the 72 hours. So pause the video now, then unpause the video when you want to go through your answer. Like mentioned before, it'll be very important that you're going to be able to draw on graphs in physics paper 3. So what you'll notice is that it's being removed every 24 hours. So we're going to have 2 more of these particular cycles, and they'll follow the same particular curve that you see previously. So it'll have the same shape as the other 2. However, they're going to be smaller values, because you should be aware that it's taken out quite a bit of it each time, so there'll be less technetium to go through. So you should be seeing peaks at 48 and 72 hours, so you'll see that added on 24 each time, and then they'll decrease in height because there's less of the sample present. Now the next question says, explain why a sample of technetium-99 is collected every 24 hours and not more frequently. So pause the video now, then unpause the video when you want to go through your answer. Right, in these types of questions, again, it's got you to think about the real world implications of what you're doing in the physics practical. So the idea is that technetium should be extracted when it's near or at its maximum activity as a result, because you get the greatest generation there collected. So as you can see, that is reached after 24 hours, which is why you should be doing, because if you take it before then, you just won't get enough of it for it to be worthwhile. Now the next question says, figure 10 shows the data from an experiment in which a copper wire was stretched by applying a known tensile force. The total extension of the wire was recorded for each value of the applied force. So again, draw a line of best fit on figure 12, then determine using figure 12 a value for the Young modulus of copper. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, firstly, to draw your line of best fit, you're going to have another well-drawn line of best fit, and you'll notice from the points here that it's going to be a linear graph to start off with, and it's then going to curve smoothly. You should know that as well from your previous understanding of the stress-strain graphs for things such as copper, that you'll be aware that it should be doing that straight line section first and then start to curve. Now again, the line should accurately follow the trend of the points and have an even scatter of points about the line. Now to work out the Young modulus, again you should know that for the Young modulus, that Young modulus is stress over strain, so it is the gradient of the line, but it has to be the gradient of the linear section of the line, because when it starts to curve, you'll no longer have the ability to calculate the Young modulus. So you've then got to attempt to measure the gradient with a large gradient triangle on the linear part of the graph. And remember, we draw that gradient triangle to show we've averaged it over a number of values. We then work it through. Now again, remember to think about stresses in times 10 to the 8 and strainers in times 10 to the minus 3. So we get our answer to be about 1 times 10 to the 11. The next question says, describe how the uncertainty in your value for the Young modulus could be estimated from the graph, and then the area under stress strain graph represents the mechanical work done per unit volume on the material as it is deformed. The original length of the wire used in the investigation is 1.50 meters and its cross-sectional area is 0.397 millimeters squared. Determine the work done on the wire as its original length is increased by 6 millimeters. So pause the video now, then unpause the video when you want to go through your answer. Right, it's important that you are aware of how you can calculate uncertainty in a number of different methodologies, with things such as repeats, with things such as readings and measurements, but also in graphs. Now it's important to know that you can work out your uncertainty by establishing the difference between your maximum gradient and your minimum gradient, okay, or the difference between the worst gradient and the best line gradient as well, and you can double it as such like that, and that allows you to work out your uncertainty. Now for this next question, you're gonna have to calculate values. So firstly, what you should be doing is, you can notice that the area under the stress strain graph represents the mechanical work done per unit volume. So what you can do is you can then work out the area and you'll get your work done per unit volume. So what you can do is you can estimate the values and work it through, and then you work out your value under the graph. Then you need to times it by the volume because it's per unit volume. Now again, if you look in the question, we've got a cross-sectional area and we've got a length, so we can then work out the volume. Now again, think of it like a cylinder. Now the trick again is it's in millimeters squared, the cross-sectional area, so you're going to have to convert millimeters squared into meters squared, and remember, it's not times 10 to the minus 3 in the conversion factor, but it'll be times 10 to the minus 6 because it's millimeters squared, so the 10 to the minus 3 is then doubled. So you can work out your volume like so and then multiply it by that value. Now again, you think, where is that area you're going to work to? As shown in the mark scheme here, it will go up to the idea that strain is 4 times 10 to the minus 3, because that's how you can work it out in the sense of, you're told the extension is 6 millimeters, so you can work out your strain by doing extension over the original length and doing 6 millimeters over 1.50 meters. Obviously convert one of them to either millimeters or meters to get your value out of strain, which is 4 times 10 to the minus 3. So work out your area up to the strain of 4 times 10 to the minus 3. Now the next question says, many cars have headlamps that switch on automatically when light levels become too low. Figure 11 is a circuit diagram showing a light dependent resistor, an LDR, being used as a light detecting sensor. The output voltage V1 from the circuit is used to control the headlamps. The resistance of the variable resistor can be adjusted to change the light level at which the headlamps switch on. The system is set to switch the headlamps on when the power of the light incident on the LDR is less than or equal to 12 milliwatts. The wavelength of the photons incident on the LDR is 550 nanometers. Calculate the number of photons incident on the LDR in 1 second when the headlamps just switch on. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, you've got to think about what values that you're aware of. So you know that you have the wavelengths. The first thing you can calculate is saying the energy is equal to hc over lambda, an equation you learnt in particles. And at that point, that gives you your energy value. Now again, remember lambda needs to be in meters, so it's 550 times 10 to the minus 9 meters. We can then say that the power is going to be the number of photons, as you can work it through, times by the energy. Now we know the power is going to be equal to 12 milliwatts, so 12 times 10 to the minus 3. So we've got an energy, we've got a power, so therefore the number of photons is going to be the power over the energy, and we get our answer out to be 3.3 times 10 to the 16. Now, figure 12 shows how the resistance RL of the LDR varies with the power of the light incident on it. V1 must at least be 8 volts for the headlamps to switch on. Determine the resistance of the variable resistor for the headlamps to switch on when the power of the light is 12 milliwatts. So pause the video now, then unpause the video when you want to go through your answer. Right, so what you've got to be able to do in this question is work out what value is needed from the graph to be working through. So straight away we can see that the value of RL is going to be 30 kilo ohms, because if we look up here we can see that the power is 12 milliwatts. So if we go up to 12 milliwatts and across on the graph, we'll see that our value is going to be 30 kilo ohms. So at this point we know that the resistance of RL, okay, is going to be 30 kilo ohms. We can then use the potential divider equation. So at this point we know from our question, if you can see here, that that the value of V1 must be 8 volts for it to switch on. So at that point, if we know that V1 is going to be 8, well therefore we know that in the variable resistor it's going to be 4, because obviously it's 12 at the start, one's taken 8, so the other must take 4. So at that point we know that V is directly proportional to R, so therefore R's value is going to be divided by 2 as such to work out our final answer, okay, and then you can work it through. So you're using your potential divider equation. Now the next question says, an engineer wants to adjust the circuit so that the headlamps switch on when the light levels are greater. State and explain what adjustment is necessary. So pause the video now, then unpause the video when you want to go through your answer. Again, this is a very common exam style question where you need to explain what's going to happen in experimental setups based on your understanding of physics. So you'll notice that how we want to adjust the circuit so the headlamps switch on when the light levels are greater. So if you have greater light levels, well then the resistance of the LDR will decrease. That's a fact, you just know. So therefore you've got to reduce the resistance of the variable resistor. And why is that? Well, that's so that the ratios of the resistances return to their original value, so that V1 returns its original value, so therefore it will switch on when you need to, because there's a potential divider circuit. The next question says, figure 13 shows the apparatus used in an experiment to measure the speed, V, of sound in wood. Two microphones, A and B, are separated by distance D and are firmly clamped face down to the wooden bench top. The microphones are covered with soundproofing foam and connected to an electrical timer. The end of the beam top is struck sharply with the hammer to produce a pulse of sound which travels through the wood. The timer starts when this pulse is detected by A. The timer stops when the same pulse is detected by B. The timer records the time t taken by the sound pulse as to travel from A to B. So explain why soundproof foam is used to cover the microphones. So pause the video now, then unpause the video when you want to go through your answer. Once again, it's a very common paper 3 style question to ask you to think about what's going on in the investigation and why certain steps are taken. Well, we use soundproofing foam to stop the microphone from picking up noises in the backgrounds or other sounds which could lead to interfering with the values that were taken. The next question says the measurement of T is repeated several times and table 1 shows the recorded values of T. Calculate the mean value of T and estimate the absolute uncertainty in your mean value of T, and the distance D is 0.75 meters. Calculate V. So pause the video now, then unpause the video when you want to go through your answer. Right, so this question is testing you on how you work out different values. So to work out the mean, you add up all the values and then divide by the number of values that you have. So in this case, it's going to be 5, but also you've always got to consider, are there any anomalous results, and they will be removed from your calculation, which you work it out to be 191. Now, how do you estimate the absolute uncertainty? Well, in this case, the absolute uncertainty when you've got a set of repeats is range divided by 2. So range is the biggest value minus the smallest value, then divided by 2, and we get plus or minus 15. Now, how do you then work if you've got a distance? How do you work out a velocity? Well, again, quite simply, we've got a time to be 191 microseconds, so 191 times 10 to the minus 6. We've got a distance of 0.75, so we can use the equation velocity is distance over time to work this out and get an answer of 3.9 times 10 to the 3 meters per second. The next question says the absolute uncertainty in D is plus or minus 0.01 meters. Estimate the percentage uncertainty in V. Then an increase in the value of D reduces the percentage uncertainty in its measurement. This increase in D also increases the value of D. Suggest why increase in D may not lead to a more accurate measurement of V. So pause the video now, then unpause the video when you want to go through your answer. Again, this is a very common question in physics paper 3. You've got to be able to calculate percentage uncertainties from absolute uncertainties. So you've got to work out your percentage uncertainty in D by doing the absolute over the value, your percentage uncertainty in T by doing your absolute uncertainty, which you calculated previously, divided by the mean value times by 100. So you've got your two percentage uncertainties there, so you should get 1.3% and 7.9%. Now, because velocity is distance over time, to then find out the percentage uncertainty of the velocity, it's the percentage uncertainty of the distance plus the percentage uncertainty of time, because they are divided by each other, so you get 9.2%. Now, the increase in D may not lead to a more accurate measurement of V, because if you think about it, when you increase the distance, you've got to think about what's happening to the sound pulse itself. So at the amplitude will get weaker, so it won't trigger the microphone B as much. So the microphone sensitivity needs to be high, so this would trigger any noise awarded with it. So whilst you do have to consider how percentage uncertainty will change with values, you've got to consider how this change would affect your measurements of those values themselves. The next question says, a fuse wire is designed to melt when the current in the wire reaches a certain value. The fuse current, IF, is the minimum current that will cause a length of fuse wire to melt. A student is provided with a length of fuse wire in normal electrical equipment. Figure 1 shows the circuit symbol for the length of fuse wire. Draw a suitable circuit diagram that the student can use to determine IF. So pause the video now, then unpause the video when you want to go through your answer. Right, again, in a paper 3 style question, you will be asked to draw circuit diagrams. So you need to have a working series circuit that will have a battery or a power supply. You'll need to think of a way in which you can alter the values in the circuit by either using a variable resistor, a variable power supply, or a potentiometer. And then you need to have an ammeter there. Now you'll notice it says how can you determine the currents. You don't need the voltmeter in there because that will be there for the potential difference. So you just need the ammeter in series. Now the next question says, the student is provided with 5 samples of fuse wire. The 5 wires are all made from the same material but have different diameters. The theory suggests that IF is related to the diameter D by the equation IF equals KD to the power 1.5, where K is a constant. So describe how the student could use the circuit that they've drawn in the question to test the validity of this equation. And your answer should include the measurements to be taken and the apparatus needed, details of the procedure, and how to test the validity of the equation. So pause the video now, then unpause the video when you want to go through your answer. it's a very common paper 3 style question to ask to write a plan to do an experiment to test out an equation that you had just been given. So to answer this question, you should really take all 3 different bullet points separately to then answer the questions in the paragraphs. So what you should be doing is, let's think about firstly about our measuring devices. So we need our screw gauge micrometer to then measure the wire diameters, because you notice that you've got diameter D in the equation, so you'll need that. We then need to measure the diameter in more than one place and in more than one direction to get our accurate results, so always consider accuracy. You'd then start with the resistor on a maximum value, and then the variable power supply on the minimum, and then increase the current slowly and record the maximum value before the wire breaks. So that's for one of the values there, and then you would repeat readings and calculate mean values for each diameter and each current. And then what you would do is you then need to plot your graph. Now this is where it's very important, because you are trying to work out a value, and you know, for example, that so you want to verify a value and you've got a power in the equation. Well, you know that if you draw a log against log graph of the 2 variables, in this case the current and the diameter in this particular equation, that the gradient of the line produced should be the power of the found in the equation. That's a very important thing to understand when you're looking at log graphs, that the log graph gradient should be the value of the power. So it's a very easy way to verify things. So you plot log I against log D, and what you should get is you should then get a gradient, a straight line with a gradient of 1.5. Now the next question says, a student is investigating the cooling of oil. She puts 250 grams of hot oil into a metal container and records the temperature theta of the oil for 300 seconds as it cools. Explain one feature of the container that will ensure a maximum rate of heat transfer from the oil to the surroundings at any given temperature difference. Draw a line of best fit for the data plotted, and explain how figure 2 together with other data can be used to determine the total heat transfer from the oil during the first 300 seconds. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question? Well, you've got to understand what things are required to have a high energy transfer. So either have thin metal walls or have a high thermal conductivity, and you could link it into an equation as shown here to then say how that is possible. Like we've mentioned before, it's a very common paper 3 style question to draw a line that best fit in for plotted data. So again, draw a nice smooth curve with the passing through all the points or near all the points with an even scatter of the points about the line. And then finally, how can you determine the total energy transfer? Well, what you've got to do is think about, what does the graph give you? Well, the graph will give you the idea of temperatures and the idea of time. Now we can see here that the temperature is changing, so therefore it's the kinetic energy store of the particles that is changing, which can be worked out with the equation Q equals mc triangle T. So what is going to be our temperature? Well, you can see it at 0 and you can work it through at 300. That then allows you to work out the change in the temperature, delta theta or delta T. You can then use the equation Q equals mc delta theta to then work out your answer of about 12,400 joules. Now the next question says, show that the rate of change of temperature of the oil at the temperature of 45 degrees is approximately 0.1 kelvins per second. Then at a temperature of 45 degrees Celsius, the rate of heat transfer from the oil is 54 joules per second. Calculate the specific heat capacity of the oil. So pause the video now, then unpause the video when you want to go through your answer. Right, again, it's a very common question to find values based on graphs given to you in paper 3. So you'll see that the rate of change of temperature is going to be temperature divided by time, which you should see is the gradient of the line in the graph, because it's y over x. But you've got a curve. So to then work out the gradient of the curve, you would draw a tangent to the curve of 45 degrees, use a large gradient triangle, and work out the value of the gradient to get about 0.09 to 0.1 0.11 kelvins per second. And remember, kelvins and degrees Celsius have the same interval, so when you're working out a change like in a gradient, it's an interchangeable unit. Now in the next one, we're trying to work out the specific heat capacity. Now we're told that the rate of heat transfer, which is the power, the work done per time, okay, is 54. So we can therefore say that power is equal to mc delta theta all over delta t. Now straight away, m and c are constants, so we can just put them to the side of the equation. So therefore P equals mc delta theta over delta t, which is the gradient of the line, which is what you just worked out. So at that point, you can then work out C by saying that C is equal to P over m times by the gradient of the line produced, and you get your answer to be about 2000 or 2300 joules per kilogram degrees Celsius. Now the next question says, figure 3 shows the apparatus that a student used to measure the wavelength of a horizontal beam of monochromatic light. The light is initially reflected downwards by a glass plate towards the lens in a mirror. The light travels through the lens and the lower surface of the lens reflects some of the light upwards. The rest of the light continues to the mirror and is reflected upwards at the mirror surface. Light from the lower surface of the lens and light from the mirror surface then superpose to form a circular interference pattern that is photographed. So figure 4 shows an actual size photograph of the interference pattern. The pattern is a series of bright and dark circles called rings. The diameter of the nth bright ring on this actual size photograph is dn. So for example, the diameter of the fourth brightest ring is d4. The student makes a magnified image of the interference pattern that is 10 times larger than the actual size. Figure 5 shows the magnified image, and the diameter of the fourth bright ring, counting from the center of the magnified image, is d4. So the student uses a millimeter scale to measure d4 from the image. The student measures d4 as 44 millimeters. Calculate the percentage uncertainty in d4, then calculate, using your answer to the previous question, the absolute uncertainty in d4 squared. So pause the video now, then unpause the video when you want to go through your answer. Right, so the first thing to note is you should see that to work out your percentage uncertainty, it's the absolute uncertainty divided by the value times by 100. Now in this case, you'll notice that it's going to be a measurement and not a reading, because you're looking at the object twice to take the value, once at the start on the left hand side and once at the end on the right hand side. So when it is a measurement, it is going to be one of the interval given. So therefore it's 1 millimeter over 44 millimeters times by 100, so the answer is 2.3%. Now it's in the next question, it's saying it's d4 squared. Now you should be aware that when you have a power in a uncertainty, that work out the final value in the percentage uncertainty is the percentage uncertainty is the percentage uncertainty of the value times by the power. So in this case it's going to be 2.3 times by 2, which gives us about 4.6%. We can then convert this back into the absolute uncertainty by working out 4.6% of 44 millimeters, the actual value. So you work it out to be 0.88. Now the next question says, determine using figure 5 an accurate value for D9, the actual diameter of the ninth bright ring. And then the wavelength lambda of the monochromatic light is given by lambda is D9 squared minus D4 squared over 20R, where R is 3.40 plus or minus 0.01 meters, which is the radius of the curved surface of the lens. So calculate lambda. So pause the video now, then unpause the video when you want to go through your answer. Right, what's very important is you've got to be able to take measurements from things given to you in exam questions in physics paper 3. So to work it through, you're going to take 2 measurements taken. So you look from one end to the other end, and I would do it multiple times. Then you can divide and find an average, and then you can work it through to be about 7.5 to 7.8 millimeters. At that point, you can sub in all the values to your equation. Again, it's a very common question to be asked to sub in values which are mostly given in a question to an unknown equation you've never seen before in physics paper 3. So you take your value for D9, which you've just worked through. Now again, you need to convert your millimeters into meters, so don't forget that. You need to get your value for D4, given previously in the questions 44 millimeters. Remember, we convert millimeters into meters. Again, we then divide it by 20 times by 3.40. Again, that's given in the question, to work out lambda to be 5.4 times 10 to the minus 7. Now, the next question then says, calculate the percentage uncertainty in your value for lambda, assuming that the absolute uncertainty in D9 squared is the same as the absolute uncertainty in D4 squared that you calculated previously. Then explain one advantage of using figure 5 rather than figure 4 to determine the value of lambda. Now, pause the video, then unpause the video when you want to go through your answer. Right, so how do you work it through? So you'll see from the previous equation that we had D9 squared in there and we had D4 squared in there. So straight away, when you've worked out your percentage uncertainties for D9 and for D4, you'll double each one. Now again, because they are subtracted from each other, you then add the absolute uncertainties when that has taken place. So we'll just have to convert that afterwards, so you can then work it through like so. So you work out your absolute uncertainty for D4 squared and D9 squared. You then add the two values together at that point, and then what you can do is then you can work out your uncertainty in R. So again, you've got your absolute, you've got your value there, so then do the absolute over the value times by 100 to get your percentage uncertainty. And again, because you've got the top value and the bottom value and the dividing, you'd add your percentage uncertainties to get your answer of 4.7%. Now the advantage is that in using figure 5 is that the absolute uncertainty in measuring D is not changing because you're still using the same measuring device and it's the same values. However, the percentage uncertainty has decreased because you're measuring larger numbers. Whenever you're measuring larger numbers without changing your measuring device, the absolute uncertainty is going to stay constant, whilst the percentage uncertainty is going to go down because you're doing an absolute uncertainty divided by a bigger number. So therefore, it will decrease your percentage uncertainty. So that brings us to the So figure 1 shows apparatus using an experiment to investigate the energy transfers when a ball bounces on a horizontal surface. The diagram shows the position of the ball when it's first released and the ball at the top of its first bounce. The ball is released from a height x and the height y of the ball's first bounce is recorded. The ball is released 5 times from a height of x of 750 mm plus or minus 2 mm. Height y is recorded each time. In table 1 shows the measurements of y. So calculate the mean value of y for the data in the table. So pause the video now, then unpause the video when you want to go through your answer. Right, it's a very common question to ask you to work out means of repeats given. So to work out your mean, you add up all the values and then divide by the number of values you've added up by. You would obviously exclude any anomalous results, but there aren't any here, so you work it through to be 497. The next question says, calculate the absolute uncertainty in y mean, and then the energy lost E by the ball during the collision with the surface is given by E equals mg/hd, where the mass of the ball is m and hd is x minus y mean. So calculate hd and the absolute uncertainty in hd. So pause the video now, then unpause the video when you want to go through your answer. Right, again, it's a very common exam style question to work out the absolute uncertainty of repeated values given. So you should be aware that to work out the absolute uncertainty in a range of repeats is with the calculation the range of the data divided by 2. So you should see the range of the data is the biggest minus the smallest value. Obviously remove any anomalous results from this, so you therefore get the range of 25. So you then divide it by 2 to get 12.5. Now this next point is asking you to work out HD and the absolute uncertainty in HD. Well, what you can do is you can then, from the previous question, you know your absolute uncertainty in Y, and you know the value of y, which you've worked out previously, and at that point what you can do is you can work out hd by doing x minus this value. So you know what your value of x is, you know your value of y mean, so you can work out hd by saying the answer is x minus y, so it's 253. Now again, what's the absolute uncertainty in that value? So what you can do is you can work out the biggest value, okay, by adding on your absolute uncertainty in y mean and then working it through like that, and then vice versa for the minimum value. That gets you your range, and then you can work out your absolute uncertainty via that methodology. Now the next question says, calculate E for mass equal 2.5 grams, state an appropriate unit for your answer. Then the absolute uncertainty in M is plus or minus 0.1 g. The absolute in the gravitational field strength is negligible, so calculate the percentage uncertainty in E. So pause the video now, then unpause the video when you want to go through your answer. Right, in this first one, we know that the E is energy. So first of all, we want our unit of energy to be in joules. So the unit's going to be in joules. Now we know the equation has been given to us. It's mg/hd, where h is going to be x minus y mean. So the first thing we need to do is just work out all the values through. So we'd work it through to be 6.2 times 10 to the minus 3 joules. So what we do is we times it by the mass, which was given in our previous question, times by gravity, which we know to be 9.81. We multiply by h, which we worked out previously. Now note for the mass given in the question, that was given in grams, so we've got to convert that into kilograms to get our answer out in joules by doing 2.5 times 10 to the minus 3. Now how do you work out the percentage uncertainty in E? Well, E is equal to mgh. So therefore, what we've got to do is we've got M and we've got H. Now G, it says is negligible, so we're fine, but because we're multiplying those two values together, we'll be adding their percentage uncertainties. So what we've got to do is we've got to work out the percentage uncertainty of M by doing the absolute over the total times by 100. We then work out the percentage uncertainty in HD by doing the absolute, which had in the absolute uncertainty, which had in the previous question, divided by the value times by 100. We then add the two together, and we get 10%. The next question says, figure 2 shows apparatus used to investigate how the frictional force acting on the block varies with mass m placed on the block. The suspended mass is increased in 50 gram increments. The largest mass that fails to move the block is noted. The smallest mass that does move the block is noted. The value of m is the minimum suspended mass that's needed to move the block and must lie within this 50 gram range. The experiment is repeated for values of mass of m, and the 50 gram range within the m lies within the recorded value of each value of big M. So figure 3 shows the data for small m and big M. The error bars indicate the uncertainty in the value of small m. So draw two straight lines on figure 3 with the maximum and minimum gradients that are consistent with the error bars. So pause the video now, then unpause the video when you want to go through your answer. So again, this question is tested on how your understanding of what error bars are and how they link into gradients. So you need to be drawing two lines. One is the maximum gradient, which is the steepest line possible, and one is the minimum gradient, which is going to be the shallowest line possible. But they've got to go through the error bars. So they've got to go through both the error bars, and you've got your minimum gradient hidden at the bottom of the error bars and your maximum gradient hidden at the top of the error bars, and that should hopefully give you your two lines. Now the next question says, determine the gradients of both of your lines. So pause the video now, then unpause the video when you want to go through your answer. Right, so for this one again, you've got your two lines here. So what you should be doing is drawing large gradient triangles and then working out your gradient by doing the change in y over the change in x. Now it's very important to note you've got to draw your large gradient triangles on the graph to indicate where you're taking your values from. Now the next question says the relationship between small m and big M is given by the equation small m is equal to mu big M plus big MB, where MB is the mass of the block and mu is a constant. The pulley is assumed to be frictionless. Determine the maximum and minimum possible values for MB. So pause the video now, then unpause the video when you want to go through your answer. Right, so how would you answer this particular question? So what you're going to have to do is you're going to have to use the graph previously to determine a value for MB. So you use the data given to get values for MB, the mass of the block. And then what you would do is you can then work it through to then determine a value of MB and then use the maximum and minimum values from the different gradients to work it through. So again, you can use the value, you can work out MB because MB you can work it through to be the intercept, because if you work through your equation, you can get MB to equal values in terms of small m and big M. So you can use then that from the gradient to work out the values, and then you can pop them into the equation. Now the next question says, figure 4 shows a transformer in a circuit with an AC power supply. The turns ratio of the transformer is NS over MP. The apparatus was used to investigate the relationship between the turns ratio and the output voltage Vs. The primary current IP and the secondary current IS were also measured. In one experiment, the input voltage Vp was kept constant and a primary coil with 100 turns was used. Table 2 shows the results from the experiment. So determine, using the turns ratio, a reliable estimate for Vp, and then calculate the efficiency of the transformer for a turns ratio of 2. So pause the video now, then unpause the video when you want to go through your answer. Right, it's a very common question in physics paper 3 to be asking to work out values from experimental results given to you. So using the turns ratio, work out what the value for Vp is. So we should know that Vp over Vs is equal to Ns over Mp. So we now have Vs and we have Ns and Mp. So what we can do is we can work out our values. So what you can do is you can work the transformer equation and you get to about 6.5. So for example, for Ns equals 50 turns, you can say 50 over 100 is going to equal 3.13 over the value of Vp, so you can then work it out for Vp. Now in theory, for the turns ratio to hold, all 3 rows should give you the same value. So as a result, you should do it from all 3 rows and indicate that there should all be the same value in your working out. Now the next question is, you've got to be aware of how you work out the transformer efficiency. So the transformer efficiency is equal to the secondary power divided by the primary power. Now you should be aware that the primary power is equal to Vp times by Ip, and that the secondary power is equal to Vs times by Is. Now it wants it for a turns ratio of 2. So straight away, okay, how can we work it through? Well, straight away we can work out our values from there, and then as a result we can work out our secondary power and our primary power by working values through like so, to then get our answer of 0.94%, 0.94, which gives 94%. Now the next question says, it suggested that the efficiency of a transformer varies with the input voltage Vp. Describe an experiment to test the relationship between the efficiency of a transformer and Vp. So your answer should include any apparatus needed in addition to the apparatus shown on figure 4, the measurements that you would take, the details of the procedure you would follow, and the details of how you would present and interpret your results. So pause the video now, then unpause the video when you want to go through your answer. Right, it's a very common question on physics paper 3 to ask you to plan an investigation with equipment you've not done an experiment with before, and they tend to sequence the answer with bullet points. Now again, to get your full marks, you should answer each bullet point separately as if it was a separate question, each in different paragraphs. So we'll go through each bullet point at a time. So any apparatus you would need will be a method of varying your primary voltage. You get different values, so you could either use a potential divider, you could use a rheostat, or you can have a variable power supply. And the idea, you'll need a voltmeter or a multimeter to measure that input voltage, because we haven't done that yet, because we only got Vs, we haven't got Vp. Now the methodology is you'd use the same primary coil and secondary coils, okay, and you take measurements for at least 6 different or 7 different input voltages or input potential differences as such. And then what you would do, as you can be aware, is you can just talk through the investigation about how you'd use your variable resistor to vary the circuit, to then vary the primary voltage, and then you can measure the secondary voltage as so, okay. And then how you process the results is you'd calculate the efficiency for each set of values. How do you do that? You do the secondary power, which is Vs times by Is, divided by the primary power, which is Vp times by Ip, and then finally you're looking to see how the efficiency and Vp link to each other. So therefore you plot efficiency that you just worked out and divide it by Vp. Again, remember just your basic ideas of always repeat the values, okay, always remove anomalous results, make sure you've got a wide range of values, okay, and you know what the measuring devices are as well. The next question says, Boyle's law states that for a fixed mass of gas at constant temperature, PV equals K, where P is the gas pressure, V is the gas volume, and K is a constant. So show that log V equals log K minus log P. So pause the video now and then unpause the video when you want to go through your answer. Again, it's a very common question on physics paper 3 to ask you to manipulate equations, especially ones that involve powers in natural logs. So what we should be aware of is as follows. If we make V the subject, we can say that V is equal to K over P. Now we know that we're going to need natural log in there, so we need to turn that into powers. So we can say that V equals Kp to the minus 1. At this point, when you want to get rid of the powers, you then add in your natural logs, which we know we need from the information given in the question. So we can therefore say natural log V is therefore going to equal natural log K times by natural log P to the minus 1. Now what happens at that point is therefore the minus 1 will cancel through, and therefore it just becomes minus 1 at the front. So therefore it'll become log V equals log K minus log P, and you've proven your answer is so. I mean, another way you could do it is by just saying PV equals K and then take log of both sides. So therefore log PV equals log K. Now again, the rule is, if you remember, that if you are logging two terms that are times together, like log PV, they can separate out but as logs for both sides, and you add them. So log PV equals log P plus log V, and so therefore log P plus log V equals log K, or if you rearrange it, you can say log V equals log K minus log P. The next question says, Figure 3 shows a circuit used to find the resistance per unit length of a copper wire. The copper wire is fixed with tape to measure to a meter ruler that has 2 mm graduations. Contact P is placed on the wire close to one end of the ruler and held firmly in place using a bulldog clip. When contact Q is placed on the wire as shown in Figure 3, the voltmeter shows a non-zero reading. Q is moved along the wire until the voltmeter reading is 0. Figure 4 shows enlarged views of the position of P and the new position of Q. Determine in meters the length of X of copper wire between P and Q. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So what you've got to see is determine the length of X of copper wire between P and of Q. So straight away you can measure the value of contact P. Now again, you're going to measure the far right hand side of P, because we're going to take it from the end point of P to the starting point of Q. So you can read it through in your 2 mm graduations to work that out. So you can see straight away that if you look on the big graduations, it goes 9, 8, 7. Okay, and then it's 2 over there, so that's going to be 6.4. Working it through like that. Okay, and then on the other side for Q, you know that it's on 91, 92, 93, 94, and then again is 94.2, so therefore you can work it all through, find the difference between the two, and then you'll see it's 0.879 meters, because we've worked there in centimeters, so we've worked out our difference, okay, which was going to be 87.9 centimeters. You then worked out that the value is therefore 0.879 meters. The next question says, when the voltmeter reading is 0, we know R1 over R2 equals R3 over R4, where R4 is the resistance of the copper wire between P and Q. Determine in ohms per meter the resistance per unit length of the copper wire, where R1 is 2.2 mega ohms, R2 is 3.9 kilo ohms, and R3 is 75 ohms. So determine that resistance per unit length. So pause the video now, then unpause the video when you want to go through your answer. Again, it's a very common exam question in physics paper 3 to determine a value when you're given an unknown equation and you're given values for that. So the first thing you need to be doing is you need to work out what the resistance is going to be. So make R4 the subject, so you can straight away see that R4 from your equation is going to equal R3 times R2 all divided by R1. Then what we do is we then make sure we convert the mega ohms into ohms. ohms by times and by 10 to the 6, and the kilo ohms into ohms by times and by 10 to the 3. And at that point we work R4 through to get 0.13 ohms, but the question wants the answer in ohms per meter. Now in the previous question we worked out the distance to be 0.879 meters, so then divide that answer by 0.879 to get our answer out to be 0.15 ohms per meter. Now the next question says the diameter D of the copper wire is approximately 0.4 millimeters. Suggest a suitable measuring instrument to accurately determine D and how to reduce the effect of random errors on the result for D. So pause the video now, then unpause the video when you want to go through your answer. Right, so again, it's really common when you ask what measuring instrument would you use to work out something, and then also how you'd use it accurately. So the first thing to note is we know that the diameter is approximately 0.4 millimeters. So we shouldn't be using a ruler for this because that value is too small to use. So we'd either be using a micrometer screw gauge, or we could be using a digital caliper. Now we wouldn't be using a vernier caliper because it'd be difficult with the actual instrument, so the shape of the object that we're given. Now how can you reduce the random errors? Well, you can reduce the random errors by repeating your investigation. Now again, when you're trying to work out the diameter, there's two ways in which you can repeat it, that you can do it at different points along the wire, and you can do it in different directions because you want to find the average value across the entire wire, and there'll be variations in the wire due to different reasons such as manufacturing errors. And the last thing to note is if you have anomalous results, you would then discard them, and then with your repeats you calculate a mean, and that then reduces your random error. Remember, repeats of measurements reduce random errors. Now the next question says, determine the resistivity rho of the copper with the diameter D of the copper wire to be 0.38 millimeters. So pause the video now, then unpause the video when you want to go through your answer. Now you should see from the equation sheet that resistivity is RA over L, or resistance per length, which is important because we just worked out previously the resistance per length, times by the area. So what we do is we've got the diameter of the copper wire. So what we know is that area is going to be equal to pi r squared because it's going to be the cross-sectional area, which is a circle because it's a wire. So we then halve the diameter to be 0.19 millimeters. We then convert that into meters because we never work in millimeters in physics, to then work out the area by doing pi r squared. We then multiply it by the resistance per length value we worked out previously, and we get our answer out to be about 1.7 times 10 to the minus 8 ohm meters. Always think to yourself in questions, what have we worked out previously? How can I link into the answer? The next question says the copper wire is replaced with constantan wire of diameter 0.38 millimeters. The resistivity of constantan divided by the resistivity of copper equals 30. Suggest one change to the circuit to make the voltmeter read 0 for the same value of X as in question 2.1. Then calculate in millimeters the diameter of a constantan wire that has the same resistance per unit length as the copper wire. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? So you've got to just think numerically about what's going on. So the idea is we want to make our voltmeter read 0 for the same value of X. So what you could do is look at what you could do for R1, R2 or R3. So the idea is, okay, because the resistivity has increased by a factor of 30, you could decrease R1 by a factor of 30, or you could increase R2 by a factor of 30, or you could increase R3 by a factor of 30. Because think about how changing that resistivity will affect the overall value, and think about how you can link it into the equation shown. Now the next one, the answer is 2.1 millimeters. Now how can you work this through? Well, what you can do is you can say that you know that resistivity is equal to RA over L. So we know that in terms of resistivity, let's just say it's 30 times greater, so you can pop that in like that. We know the difference is going to be with the same resistance per unit length, so therefore R over L is going to just cancel through. So therefore we know that it's going to be equivalent to D squared fundamentally, because the only factor left that can vary this resistivity up by a factor of 30 is going to be the area, which links into diameter squared. So what we can then do is we can work out the change in diameter, and we get our answer out to be about 2.1. Now the next question says, figure 5 shows two loudspeakers, A and B, that act as a coherent point or sources of sound of a single frequency. C is the midpoint between A and B, and distances OA and OB are equal. QP is perpendicular to CO, and the student uses a sound level meter to measure the intensity of the sound. The meter detects a maximum intensity at O. The student moves the meter along OP, and the intensity decreases and reaches a first minimum at M. The intensity then increases as the meter moves towards P. The student records AB to be 1.80 meters, CO to be 8.00 meters, and OM to be 1.24 meters. So show that the difference between path lengths AM and BM is approximately 0.3 meters. So pause the video now, then unpause the video when you want to go through your answer. It's not uncommon in exam questions for you to be having to work out values based on trigonometries and diagrams given to you and the values stated for you. So you should see from the diagram that you can see that AM is squared is going to be equal, if you can see here, okay, to AO squared plus will be OM squared, like so. So what you can do is you can work it through by saying, well, AM squared is going to be equal to 8 squared, which is going to be AO, which is the same as CO because it's a parallel line acting upwards, and the difference from OM. Now you know the answer is going to be 0.34 because you can see from 1.24 meters and you can see from 0.9 meters what that difference is going to be. So you can see it's going to work through to be 0.34 meters. So you're just looking at the values on the diagram, so you can therefore work out AM to be therefore 0.27 meters. The next question says the speed of sound is 340 meters per second. Determine the frequency of the sound waves. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, you should hopefully be aware that the path difference is going to be lambda over 2, okay, because they are coherent points of source of a single frequency, and as you can see that they're coherent, so therefore it's going to be lambda over 2. So what you can do is therefore you can get your answer to the previous question, okay, which is going to be your path difference, and then work it through to be working it out to say that it's going to be 300, work it through to get your answer out to be saying its wavelength is 2 times by the answer previously, and then we can say that 340 over lambda is going to equal your frequency. So therefore, because we know that V equals F lambda, so therefore F is going to be V over lambda, so it's 340 over the wavelength you just calculated to get approximately 570 or 630 hertz. Now the next question says, figure 1 shows apparatus used to determine the acceleration g due to gravity by a freeform method. When the switch is opened, a timer starts and a steel ball is released from rest. The ball falls vertically onto an impact switch and this stops the timer. The timer displays the time t for the ball to fall through the vertical distance s shown in figure 1. A student obtains values of t for different values of s. The student plots the graph of 2s against r squared as shown in figure 2. So the student has used an absolute uncertainty in S to draw the vertical error bars in figure 2. Deduce the student's absolute uncertainty in S and then determine the maximum gradient G max of a straight line that passes through all the error bars and the minimum gradient GM of a straight line that passes through all the error bars. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, you can work out your absolute uncertainty, okay, by just understanding that the absolute uncertainty is the range of the error bars divided by 2, because it's a visual representation of the range. So therefore you look on your graph and you can see that the difference is 0.08 meters, so divide that by 2, it's 0.04 meters. Now the next question, you should be drawing 2 straight lines in. Now you can see that G max is going to be the steepest line, as you can see here, because it's the maximum gradient, so it's going to give us the maximum value for the gradient, and that G min is going to be the shallowest line possible. Now again, it's really important that when you draw these lines you hit all the error bars and don't miss out the error bars. So you can see that you're clipsing the bottom of the error bars and then the top of the error bars, and they swap over to give you that steepest value and that shallowest value. Then when you've got your lines of best fit in, you can then work out your gradients of each by drawing gradients gradient triangles of each one. The bigger the gradient triangle, the better. Divide y by x and you get out your value. So G max should be about 10.7 and G min should be about 8.7. Now the next question says it can be shown that 2s equals gt squared. So determine a value for g using g max and g min, and then determine your percentage uncertainty in your value for g. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this first question? Well, you can say that your value for G is going to be the average of G max and G min, because that's the biggest possible and the smallest possible value. So the first thing you note is that G is going to be G max plus G min divided by 2. That gets you your value of G. So at that point you can work it out, and again remember it should be to two significant figures because that's how many values your question was given to. So you should be getting about 9.7. Now your percentage uncertainty is your absolute uncertainty in G. Now your absolute uncertainty in G is going to be the range divided by 2, which is the G max minus the G min divided by 2. That then gives you your absolute uncertainty. So therefore it's going to be the change divided by the value times by 100 to get your percentage uncertainty out, because percentage uncertainty is always the absolute divided by the average value times by 100. Now the next question says a fault develops in the apparatus. When the switch is open, there's now a 30 millisecond delay before the ball is released. So state the type of error produced by this fault. Then the graph of 2s against t squared is produced when using results from the faulty apparatus. Describe how this graph is different from the graph in figure 2. So pause the video now, then unpause the video when you want to go through your answer. Right, it's very important to know the two types of errors. So an error which is the same for every measurement is called a systematic error, and an error which varies for measurements is called a random error. Because you've got the same error each time, there's 30 milliseconds delay, it must be a systematic error. Now how would this systematic error affect your results? Now what you've always got to remember is that the systematic error will not affect the gradient in most cases, but rather it'll affect the y-intercept or it'll affect the x-intercept, depending on the value that's being measured. Now the value that's being measured is the time, and that's where the systematic error is, so it's going to cause an issue in the value. So what you'll notice is the points will all be displaced further to the right because all the values for t will be bigger than they should be, so it'll affect where your x-intercept is. So therefore as well the y-intercept will also decrease because they've all been shifted across, so it's going to hit the y-intercept at a lower value. But it's important to note that the systematic error will not affect your gradient, so it'll still have the same steepness for your gradient. So that brings it QA A-level physics. So the first question says a temperature sensor is connected to a data logger to monitor how the temperature of a fixed mass of recently boiled water varies with time t over an interval of 600 seconds. These data are processed to produce the graph shown in figure 10. Determine the temperature of the water when t is 190 seconds. Determine the gradient G1 of the graph at t is 90 seconds, and then when t is 370 seconds the temperature is 46.6 degrees Celsius and the gradient G2 is minus 0.0645. Evaluate theta r. So pause the video now, then unpause the video when you want to go through your answer. Right, with this type of question, it's all about interpreting graphical information. There's nothing you can do here about the practical, it's all about interpreting data from this graph. So the first thing is to work out theta 1 when the temperature is equal to 90 seconds. So what you would do is you would go along to 90 seconds on the x-axis, look up on the graph and move across the y-axis, and you'll see it's about 61 degrees Celsius. Now the next one is determine the gradient G1 at time is 190 seconds. So you're going to have to work out the gradient of your graph, but it's a curving graph, so we need to draw a tangent. So you should be drawing a tangent which intersects the line at 190 seconds. You then draw your right angle triangle in on your gradient and you get your value to be minus 9.57 times 10 to the minus 2. Now it's important to note it should be a minus value because the graph is going downwards. Now in the last one you've got to work out theta r. Now you are given an equation for this. Now it's important to note you were given G1. So you've worked out G1 from the previous question, you've got theta 1 from the previous question as well, you're told theta 2, you're told G2, so it's a case of popping in all the numbers and working it through to get 17.3 degrees. Now the next question says, it can be shown that when a hot object at temperature theta is allowed to cool in a draft, the rate at which the temperature decreases is directly proportional to the temperature difference between the object and the surroundings. A student realizes that this will decrease exponentially with time and designs an experiment in which two temperature sensors are connected to a data logger. Sensor 1 is placed in a beaker of recently boiled water. Sensor 2 measures the air temperature in the room. The data logger is programmed to record the output from the sensors as the water cools for 600 seconds. The output data from the sensor is processed to produce the graph as shown in figure 11. So this change will decrease exponentially in the same way as the potential difference across the discharging capacitor decreases with time. When a capacitor discharges, the PD across the capacitor falls to 1 over E of an initial value of a time called the time constant. Electrical engineers assume the capacitor becomes fully discharged in a time equal to 5 time constants. Estimate the time taken for the water to cool down to room temperature. So pause the video now, then unpause the video when you want to go through your answer. Right, for this question, it is trying to link in capacitors and exponentiality, but it's a case of just using the graph available to you. So what you've got to do is consider what theta and minus theta r is going to be. So you've got to correctly evaluate that. So you look on your graph and theta 0, the starting temperature is 89 degrees Celsius, and then theta r, you can work out on the graph, it's the line when it's going directly along, because that's measuring the room temperature in the room, so therefore that is 21 degrees Celsius. So theta 0 minus theta r is going to be equal to 68 degrees Celsius. Now we can then divide that by E, because we're saying it falls to 1/8 of the value, so we can work that through, and then we also obviously will add in our value, so we can say, well, the difference is 68, we divide it by E to get 25, we then add in our room temperature again, because we're looking at the time taken to cool down to room temperature, so therefore we do 25 plus 21 equals 46. Now it also indicates to us how can we work out what our time constant is going to be. Well, then we can work up by using the axis, we can work this off, so we know that it's the time taken to fall by 46, so therefore what we do is we go from 89 to 46 and work out that particular 89 to the 46 value there. So what you can do is read through the graph, and you see on the graph that to go to that particular value, it is about 390 seconds. Now at that point, that tells us what our time constant is. So we've worked out our time constant to be 390 seconds. Now it says in the question, it says the time for it to fully cool down is equal to 5 time constants, because that's the time it takes for it to be fully discharged. So we then multiply our answer by 5, and we get an answer of about 1950 seconds. The next question says, another student carries out the experiment using the same mass of recently boiled water and a beaker as before. The output data for sensor 1 from the student's experiments are shown in figure 12. Account for the differences between these results and the way they are displayed with those shown in figure 11. You should include appropriate quantitative data in your answer. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, it's looking at how it was different to our previous graph. So pretty much what you're doing is you're looking at the graph in the previous question, and you're looking at this graph, and you're going to just talk about the differences. Now, like it says in the question, it wants quantitative data, so give numerical values. So let's look at the two graphs and how they're different. Firstly, the starting temperature is lower. Second, so the starting temperature in this one is 86, whilst in the previous one was 89 degrees. It also indicates to us that it's leveling off at the room temperature, and we know here it's leveling off at about 37.9 degrees. So as a result, the room temperature therefore is higher, and therefore the draft is also less, because it's not decreasing as quickly, because it only cooled by 38 degrees after 600 seconds. So therefore we can indicate that that was an issue. Now the other thing is to note and look at the graph, so you can tell quite quickly that the sample rate of the data logger was longer, because you've got these discrete drops as we're going through it. So the samples here you can see from your graph are recorded every 20 seconds. You can see it by the drops which they take place. So therefore the original experiment didn't have these drops, so therefore it's much higher. So you've got to be able to compare and contrast data. The next question says, to reduce the impact of random error, the student takes several measures of a diameter at different points along a wire so that he can calculate a mean value for D. These measurements are shown in the table. Use the data from table 3 to determine the percentage uncertainty in the student's results for D. So pause the video now, then unpause the video when you want to go through your answer. Right, to work out percentage uncertainty when you're given a set of repeats is you've got to firstly work out the mean value by adding up all the values and dividing by the number of values that you've got, but also bear in mind you exclude anomalies if there are any. I don't believe there are any in this experiment. So you work out your mean to be 0.57 millimeters. Now the uncertainty and the absolute uncertainty for repeated values is going to be half of the range. So the range is the biggest number minus the smallest number, and you do half of that, and therefore to work out your percentage uncertainty, it's your absolute uncertainty, which is half of the range, divided by the mean, times by 100, which is 0.70%. The next question says, this question is about an experiment with a retractable steel tape measure. The tape measure is placed at the edge of the bench and about 1 meter of the steel tape is extended so it overhangs the bench. The tape is then locked in this position to stop it from retracting. A student measures the dimensions x and y and the horizontal and vertical displacements of the free end of the tape are shown in figure 7. So describe a suitable procedure that the student could measure y, and then by changing the extension of the tape the student obtains further values of x and y. Suggest why the student chose to make all measurements of x greater than 70 centimeters. So pause the video now, then unpause the video when you want to go through your answer. Right, for this question you're just going to consider the information and think about how you can get an accurate value of y. So the technique you would do is you would have a meter ruler made vertical with a set square in contact with the floor to ensure that the ruler is vertical. You would then measure the height from the free end of the tape to the height of the tape above the bench, and the y is the difference in these heights. Or you could use a meter ruler or a straight edge along the actual bench so you can see what the straight edge will be, and then use an additional ruler to ensure that you can measure that difference between that and the end of the ruler, the end of the tape. But you've also got to always think, how can you make your ruler vertical? So you've always got to talk about making them vertical by using a set square. Now this next question is asking you to consider why you do certain things in experiment as an experimental technique. And the important thing to note is you want to use values above 70 centimeters because it will decrease the percentage uncertainty, because your absolute uncertainty is fixed, but when you divide it by a bigger value you're going to get a lower percentage uncertainty, because percentage uncertainty is absolute divided by the value times by 100, so therefore you'll get a lower percentage uncertainty, not absolute but percentage. So when you're changing the values you're measuring, it tends to be to change the percentage uncertainty. The next question says, the data from the experiment suggests that y is equal to ax to the power n, where n is an integer and a is a constant. The data is used to plot the graph in figure 8. Determine n used in figure 8. So pause the video now, then unpause the video when you want to go through your answer. Right, it's important to note that when you've got a log y against a log x graph and you're going to have y ax to the power n, it's important to note that this tells you that the gradient is actually going to be the power of the x, the power which is next to x, so x to the power n, so n is in fact going to be the gradient of the line. That's an important fact you've got to know for a log y against log x graph. In that format, the gradient of the line is going to be the power value on the x value. So what you've got to do in this question is draw in your correct line of best fit, and you can see on the screen where it tells you to place your correct line of best fit, and you're then going to work out your value for n by working out the gradient, and obviously you'll round it to the nearest integer. Why is that? Because it tells you in the question that n is an integer, so therefore you should be getting n is equal to 4. The next question says, explain how the numerical value of a can be obtained from figure 8. So pause the video now, then unpause the video when you want to go through your answer. Right, so as well as being able to understand on a log y against log x graph what the gradient represents, it's important that you can also work out what the value multiplied by the x value is going to be. Now, how you can work it through is as follows. You would know that the y-intercept will be equal to log a. So what you can do is you can draw in your line and derive what the y-intercept is, and at that point we can say that equals log a, so therefore you can reverse that by saying, well, you can then work it through by saying A is equal to 10 to the power of the y-intercept. So you would work it through like that and get your answer through. So when you work it through, you can probably get your y-intercept to be about 0.73, 0.74. So therefore A is equal to 10 of the power 0.73. Now it's important that this is the case because we know log y is equal to n log x plus log a. So that tells us that our y-intercept, when of our equation y equals mx plus c, that our plus c is going to be log a, so that's how you can work out values of a in this context. The next question says, estimate the order of magnitude of a and use this data from the table, okay, to give your answer with an appropriate unit. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, we can work out that we said before that we say y is equal to ax to the power of n. So what we can do is we can then change this round to make a the subject. So a therefore is equal to y over x to the power of n. Now it's important to note that in the question we have previously worked out what n is. N is equal to 4. It's the gradient of the line. So what you can then do is for all of the values you can work it through by saying for any of the rows you could just do 61.2 over 132.4 to the power of 4 and work out your value like that. And then you can see from the graph they're all going to be to the magnitude of 10 to the minus 7. So the answer is going to be 10 to the minus 7. Now it's asking what the unit is going to be. Well, we'll notice that y is in centimeters and x is in centimeters, but the power of x that x is multiplied to is to the power of 4. So we're actually saying it's centimeters over centimeters to the power of 4. So therefore when we work it through and cancel it through, it's centimeters to the minus 3, and that's the units being given. The next question says, this question is about an experiment to estimate absolute zero. Figure 9a to figure 9d shows the stages of the procedure carried out by a student. An empty flask fitted with a tube and an open valve is placed in water bath H containing hot water. The air inside the flask is allowed to come into thermal equilibrium with the water. The valve is then closed, trapping a certain volume of air as shown in 9a. The flask is inverted and placed in water bath C, in which the water is at room temperature. The air inside the flask is again allowed to come into thermal equilibrium with the water as shown in figure 9b. The valve is opened and some water enters the flask as shown in 9c. The depth of the inverted flask is adjusted until the water level inside the flask is the same level as the water in the water bath. The valve is then closed, trapping air and water inside the flask as shown in figure 9d. So estimate the volume of air in the flask in 9c and is less than the volume of the air in the flask in 9d. So pause the video now, then unpause the video when you want to go through your answer. Right, so it's talking about, well, what's actually going on in this situation. Now we're thinking about pressure in this situation and temperature because we're linking it into the volume of a gas. So we can say that y is the volume of air in C less than the volume of air in D. Well, when you look at the situation and what's actually going on, you can see quite clearly that the pressure of the air in C is going to be greater than the pressure of the air in D, or you could argue the vice versa. And so therefore, because the temperature is the same, we know what Boyle's law is. PV equals a constant. So we can say that when pressure increases in one, volume decreases in another to keep the value constant, and so therefore that's why the volume will change. The next question says, explain why Charles's law can be applied to compare the air in the flask in 9a with the air in the flask in 9d. So pause the video now, then unpause the video when you want to go through your answer. Right, well, this question is asking you just to basically understand what Charles's law is. So it's the idea that here the mass of the air in both of those beakers is going to be the same because they've not been adjusted, and they've got the same pressure. So therefore, any suggestion that the temperature is constant, that the volume is constant, and that the pressure is therefore changed. So therefore, it's the idea that there's the same moles of gas there, the same amount of gas there. So therefore, you've got to understand that if the temperature is constant, then the volume will be constant. The next question says the flask is removed from water bath C and then the valve and the stopper are removed. The volume of the flask is V1. The flask is then completely refilled with water and the valve and the stopper are replaced. The volume of water in the flask is now V2. The volumes V1 and V2 are shaded in parts figure 10. Explain how V1 and V2 can be determined. In your answer, identify the suitable measuring instrument and the suitable procedure to eliminate a possible systematic error. So pause the video now, then unpause the video when you want to go through your answer. Right, well, in these types of questions, it's always trying to work out what is being asked of you. And fundamentally, what they're asking you is how can you measure volume of water, of a liquid. So what would the method be? So you would probably use either a measuring cylinder or a graduated beaker. So what you would therefore do is you would get the liquid, you would then pour it into the measuring cylinder or the graduated beaker, ensuring it's on a flat surface, and then you would then measure the level that the volume rises to with the eye level with the bottom of the meniscus point in your water liquid. So this will be there to avoid parallax error, because if you weren't looking directly parallel with the water level, well, therefore you would have a parallax error. So it's important here, it looks a very challenging question, but all it's asking you to do is how do you work out volume of a liquid. So I hope you've enjoyed. So let's now have a look at practicing some practical skills questions for paper 3 in AQA A-level physics. The first question says, figure 5 shows the apparatus used to investigate the bending of a beam. The beam is placed horizontally on rigid supports. Distance L between the supports is 80 centimeters. A traveling microscope is positioned above the midpoint of the beam and focused on the upper surface. Figure 6 shows an enlarged view of both parts of the vernier scale. The smallest division on the fixed part of the scale is 1 millimeter. What is the value of the vernier reading R0 in millimeters? So pause the video now, then unpause the video when you want to go through your answer. Right, it's an important skill that you can be able to read the vernier scale. Now it's important to note that when you are reading your vernier scale, the first value that you take is just going to be the whole number value, and that's going to come as it's the value, it's the last value before the 0 starts. So you'll see on this particular scale that it goes 35, 36, 37, then there's 0, then there's 38. So we can tell straight away that it's going to be 37. Now the next thing is it's going to be 0.8, because then what you do is to find the next point, the decimal place on your vernier scale, is to then see when the points are aligned between the vernier scale and the normal scale. So you'll see that 1, 2, 3, 4, 5, 6 and 7 aren't aligned with the scale, but 8 is, so it's 37.8. The next question says, figure 7 shows the beam bending when a hanger of mass 0.050 kilograms is suspended from the midpoint. The microscope is refocused on the upper surface and the new vernier reading R is recorded. The vertical deflection S of the beam is equal to R minus R0. The total mass suspended from the beam is increased in steps of 0.050 kilograms, and a value of S is recorded for each M up to a value of M equals 0.40 kilograms. Further values of S are then recorded as M is decreased to 0.050 kilogram steps until M is 0. Student A performs the experiment and observes that the value of S during unloading are sometimes different from the corresponding values of loading. State the type of error that causes the difference student A observes. So pause the video now, then unpause the video when you want to go through your answer. Right, so for this type of question, you've got to understand what type of error it's causing. Now, there are two major categories of error you can think of, which is a systematic error, which is the same error on all results, or a random error, which is a different value for all particular readings. Now, in this case, you'll notice that the student sometimes gets different values, so therefore it isn't on every value. So because it's only sometimes, it has to be a random error, not a systematic one. The next question says, student B performs the experiment using a thinner beam but with the same width and made from the same material as before. Discuss one possible advantage and one possible disadvantage of using the thinner beam. So pause the video now, then unpause the video when you want to go through your answer. Right, in this type of question, you've got to think about how it will affect all parts of your particular value. So the first advantage is if you use a thinner beam, you're going to be having larger values of extension being taken place, because it's a thinner value, so it'll be easier to extend or bend more. So therefore, we've got larger values of S, so the percentage uncertainty in the value is going to be reduced, because we're getting larger values with the same absolute uncertainty, so our percentage uncertainty goes down. But the disadvantage is it's undergoing so much extension, this relates back to your knowledge of materials, is that it's now going to undergo plastic deformation or inelastic deformation. So the graph will not be linear, it will be curved, or you could also say that the beam may break, or the actual beam may slip off the supports. And finally, you could also say that if you have a thinner beam, you can't use as many masses, because if you then have a same range of mass with a thinner beam, it might snap before then. So they're all possible errors that could take place. The next question says, figure 8 shows the best line fit produced by the data collected by student A. It can be shown that S equals nm over E, where E is the Young modulus of the material and n is a constant. So deduce in seconds to the -2 the order of magnitude n, where E equals the Young modulus 1.14 gigapascals. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, the first thing to note is with the Young modulus, it is actually going to be 1.14 times 10 to the 9 because it's in gigapascals. So that's very important that we know that. Now we're trying to work out what S is, so and we're going to do then S to the -2. So how can we then work it through? Well, we can rearrange it and make n the subject. So we can say n is equal to SE over m. And then what we can therefore do is, if we know S is equal to nm over E, well, therefore we can calculate the value by looking at the different values that we can get. So we can say n is equal to SE over m. So we can therefore work it through by saying, well, S over m is going to be the gradient. So because we know from the graph, gradient is y over x, so we can work out what the gradient is going to be, pop in the numbers, and therefore we can work out what it is, because we know what E is as well. So we should hopefully get the correct answer. So it should be in the order of magnitude 10 to the 8. Now, the next question says, figure 9 shows that log 10s varies linearly with log 10l. State what this shows mathematically about the relationship between s and l. Don't do a calculation. Then deduce using figure 9 the value of s when l equals 80 centimeters. Then determine m using figure 8. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? So the first question is looking at what's the relation between S and L, but it's going to be log S and log L as they vary linearly with. So therefore what we can say is that S and L are linked by the power law, because what we can say is that when you've got a logarithm involved and you're getting a linear relationship, that they must be linked by an actual power. So you could say S is directly proportional to L to the power of something. So for example, it could be S is directly proportional to log to the power 3. Or you could say S is equal to KL to the power 3. So you can work it through like so. Now then, using figure 9, what the value of S is when L equals 80 degrees. So what you can therefore, 80 centimeters, sorry. So what you can do is, because we know we've got log L, so what we can do is we can work out what the value of log L is when we can work this through. So what we can do is you can work out what log L is, so work out log L is going to be equal to minus 0.097. So we can work that through, as it's going to be the y-intercept, so you can work it through like that. And at that point we can work it out, sorry, not the y-intercept, my apologies. Okay, it's going to be the value on your particular graph there, so it's going to be minus 0.097. So therefore what you can therefore do is then use figure 9 here to work out what S is going to be, because you can work it across and then you can link it in as such. So therefore you can get your value to be about 3.1 times 10 to the minus 2. Be careful that we're using log 10 as the base, not a natural log, so it's log 10, otherwise you won't get the right answer. Now finally, how do you work out m? Well, what you can do is, in the previous question you got the equation for m, so you can work it all through because you've got your different values of L, S and E, so you can work it all through to work out what m is. So it's going to be the value you just worked out before times by the gradient, which is going to be log S over log L. Now the next question says an analog voltmeter has a resistance which is much less than that of a modern digital voltmeter. The analog meter can be damaged if the full scale reading is exceeded. Figure 6 shows a dual range analog voltmeter with a zero error. The voltmeter is set to a more sensitive range and then used in the circuit. What is the potential difference between the terminals of the voltmeter when a full scale reading is indicated? So pause the video now, then unpause the video when you want to go through your answers. Right, so how do you answer this particular question? Well, you got to think in this particular question, you're looking at what the biggest value is going to be, okay, and working it through like so. So what's the potential difference between the terminals when the full scale reading is indicated? So you're going to have to work out what the biggest possible value is when you're working this through. So we're using the more sensitive range that's used in the circuit, so therefore we're going to use the lower one, because as a result you can see that it's going to be climbing upwards like that. And then it also says that the reading can be damaged when the full scale reading is exceeded, so therefore our value is going to be 2.7, because the biggest value you can get to is 3, but you want to be going to the one before that, so therefore we're looking at 2.7. Now the next question says, explain the use of the mirror when reading the meter. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this question was all about experimental technique. So you've got to think, why do you need the mirror there in terms of you're using an analog scale? So you're looking at a actual measuring point on a scale. So you move the position until the needle is aligned with the reflection in the mirror. So something like that. So you're using it, so you move the position until the needle is aligned with the reflection. So we therefore know we're looking at it dead on. Now why do we want to look at it dead on? We want to look at it dead on to reduce the effect of parallax error, because parallax error is when you don't read the scale directly from above, you're looking at an angle. Well, it can't be at an angle if the reflection is in line from the mirror with the actual needle pointer. The next question says, this question is about the determination of the Young modulus of a metal wire. In an experiment, two vertical wires P and Q are suspended from a fixed support. The fixed part of the vernier scale is attached to P and the moving part of the scale is attached to Q. The divisions on the fixed part of the scale are in millimeters, and an empty mass hanger is attached to Q and the scale is set to 0. A load is added to the mass hanger so that the extension of Q can be measured as shown in figure 1. The reading on the vernier scale can be used to determine the extension of Q. Then figure 2 shows how the extension varies with M. The mass is added to the hanger. Determine the mass added to the hanger shown in figure 1. So pause the video now, then unpause the video when you want to go through your answer. Right, so how do you answer this particular question? Well, the first one, we're trying to use figure 1 here to work out what our extension is. So we're going to have to use our vernier scale measurement, our vernier scale here, to work out the different values between the value on the left and the value on the right hand side. So when we use our vernier scale on the left hand side, we can see quite clearly that when we're working this through, we're going to get a value out, okay, at the Z. Well, if you look on it, you're going to be looking at 0. If we look at the alignment of their 0.1 between the two scales there, and then on the extension, the second one, we're looking at the value to be 2.8. So at that point, because 2.8 aligns on the right hand side and 0.1 aligns on the left hand side, we will do 2.8 minus 2.1 minus 0.1, and so therefore the extension is the difference, so it's 2.7. It's really important you can read vernier scales correctly. Now the next one, determine the mass hanger shown in figure 1. So how can we work this one through? Well, we can work out our mass to be 5.8. Why is it 5.8? Well, because we've just worked out what the extension is going to be. We've worked out our extension is 2.7. So therefore we go up on our graph to 2.7 on the y-axis, read across, read down, and we get our x-axis value to be 5.8 kilograms. The next question says, a student uses digital vernier calipers to measure the diameter of Q. She places Q between the jaws of the calipers and records the reading indicated. Without pressing the 0 button, she removes Q and closes the jaws. The views of the calipers before and after she closes the jaws are shown in figure 3. Calculate the true diameter of Q. So pause the video now, then unpause the video when you want to go through your answer. Right, so what do we do here? We've got to be able to work out what our diameter is going to be when measured, but we've obviously got a 0 error because we're reading minus 0.07 when the jaws of the caliper are closed. So they've got a 0 error of minus 0.07. So we should always minus the 0 error from our particular reading, which is 0.44. So when we minus 0.7, we're adding 0.07, so the value is 0.51 millimeters. The next question says, the student repeats her experiment using a wire of the same original length and metal but a smaller diameter. Discuss two ways this may affect the percentage uncertainty in her result for the Young modulus. So pause the video now, then unpause the video when you want to go through your answer. Right, in these types of questions, it's always very important you think of all the factors in the particular equation and see how changing the diameter will affect those values in your Young modulus. So the first thing to note is that when you use a smaller diameter, you get a larger extension. So this will reduce the percentage uncertainty in the extension, so therefore reduce the percentage uncertainty in the Young modulus. But using a smaller diameter will increase the uncertainty in the cross-sectional area part of the Young modulus measurement, because we know area is pi r squared and diameter is r over 2. So therefore it will increase the percentage uncertainty. Now, in addition to that, you'll have another factor. It's that when you've got a lower diameter, therefore the y will reach its limited proportionality a lot faster, or be more likely to, with the masses that you're going to do. So therefore you won't be able to get high enough range of readings for your mass, which will be important when you add it, because you can say when you're working out your Young modulus, you need your force, which links into your mass, because F is going to equal mg in this instance. So therefore it'll increase the percentage uncertainty for that value, so overall it'll increase the percentage uncertainty for your Young modulus. Always consider all the factors in the equation for a particular value. The next question says, a student decides to carry out a similar experiment. The student thinks the meter in figure 7 could be used as a microvoltmeter to measure E, the EMF. When this meter indicates a maximum reading and the needle points to the right hand side of the scale, the full scale deflection, the current in the meter is 100 microamps. The meter has a resistance of 1000 ohms. Calculate the full scale deflection of this meter when used as a microvoltmeter. Then the scale on the meter has 50 divisions between 0 and the full scale deflection. Discuss why this meter is not suitable for carrying out the experiment. So pause the video now, then unpause the video when you want to go through your answer. Right, in this one, how to work out the full scale deflection? Well, what we've got is we know the full scale deflection is going to be when you get to the end of the scale, which is going to be at 100 microamps. And we know that the resistance is 1000 ohms. So what we can therefore do is we can say that, well, V equals IR, we know that equation, and therefore we know that it's going to be 100 microamps times by 1000 ohms. So therefore we get 10 to the 5 microvolts. Okay, and remember we want to work in microvolts because that's what the unit is given in the question. Now, will this be a particular suitable scale? Well, no, it's not, because the resolution is not going to be satisfactory, because the largest PD will be measured will be less than 1500 microvolts. So therefore you're only using about 1.5% of the range. So therefore you won't be able to really use it very sensitively, and it won't get a very good result. The next question says, this question is about an experiment to determine the internal resistance of a power supply. The student is given a circuit and the 4 resistors of known resistance in figure 1. The student can change the external resistance R of the circuit between terminals X and Y. This is done by connecting different combinations of 2 resistors in series or in parallel between X and Y. This method can produce 12 different values for R. Calculate the largest value of R that the student can be obtained using 2 resistors. Then calculate the smallest value of R that the student can be obtained using 2 resistors. So pause the video now, then unpause the video when you want to go through your answer. Right, this question is relevant by the fact of you need to know the circuit laws, and that is when you add resistors in series the value goes up, but when you add resistors in parallel it goes down, because 1 over RT equals 1 over R1 plus 1 over R2. So to find the largest value resistance that from 2 resistors, you add the 2 biggest ones. You can see in series you just add the 2 values and you get 15 ohms. Now to find the smallest one, what you will do is you will add 2 values but in parallel. So what you will do is you need to select the 2 smallest values and you still then place them in parallel, because when you add them in parallel it decreases the resistance even more. So you get the 2 smallest values anyway and then add them in parallel. So you say 1 over R total equals 1 over 2.2 plus 1 over 3.9. You work it through and you get 1.4 ohms. The next question says, figure 2 shows one particular combination and arrangement of 2 resistors that the student could use. When S is closed, the voltmeter reading V is 1.14 volts. Explain why V is less than 1.62 when S is closed. So pause the video now, then unpause the video when you want to go through your answer. Right, once again, this is linked to you understanding the idea of internal resistance, because when the switch is closed, you'll notice that the circuit then is complete, so then current can flow. At that point, the voltage will drop because there will be lost volts due to internal resistance. So as the EMF is then produces the PD to flow through the circuit, you're then going to get your internal resistance, you're going to get lost volts, so therefore the value will not be as big as it would be for the EMF. The next question says figure 4 shows a different method for varying R resistance described to the previous question. The 4 resistors are connected in a loop with sockets A, B, C and D at each junction. 2 leads are used to connect the resistor loop to X and Y. Discuss whether this method is an improvement over the method described in the previous question. In your answer, refer to the number of different values that can be obtained for R. So pause the video now, then unpause the video and you'll want to go through your answer. Right, well in this question it indicated to you, okay, that we need to work out how many values we can determine. Now in the figure 1 method it said you could get 12 different values. Now in this particular method you can only get 6 values. So you can note here, okay, that you can only get 6 possible combinations of getting the resistors in there by looking at the different circuits. So therefore when you notice that you can only get 6 values for R by this method, it won't be as good because figure 1 can get 12 different values. So because you can get more values, you're going to get a better experimental results, so it's important that that is recognised as the reason why figure 1 method is better. So I hope you've enjoyed this particular revision session and you've learned in this revision session. Hopefully if you've learned this revision session you can answer A-level physics paper 3 examination style questions. You can assess your understanding on A-level physics and understand what topics you need to improve upon for paper 3 and AQA A-level physics.